Hi guys, today we will be discussing about the absorption of light and the Lamberts law, which deals with the absorption of light. So first of all, before starting this topic, we'll see how practically we can measure, how can we measure the absorption practically. So generally there is an instrument which is known as the spectrophotometer, which is the instrument that is used for measuring the absorption of light. The instrument's name is spectrophotometer. So what happens in this meter is that we'll look at how is the setup and the design of this meter. Generally you can measure the absorption of either a solution or you can also measure the absorption of a film. Film means a small layer of a coating that you do on a glass. So let's say you have a semiconductor and you want to find the absorption. Generally what we do is that we'll take a glass, transparent glass, and then we'll coat this semiconductor as a very thin film on this glass. So we'll coat it onto this glass as a very thin film. Yeah, so once you have coated this onto this glass, you can measure what is the absorbance. So we'll see how this can be done. So the spectrophotometer has two light source which gives the same light. So let's say you have a light source, and then what we do is that if we are taking a solution, we'll take it in a cuvette. So cuvette is like this, I mean a kind of a rectangular kind of a small rectangular shaped bottle, not a bottle but yeah, so which can hold solutions, let's say in this fashion. So yeah, so I think it is clear. So in this you can take any kind of a solution. Let's say if you are dealing with dye sensitized solar cells or solar cells with where you're going to coat a solution, or what we can do is that you can find what is the absorbance of this particular solution. In the case of dye sensitized solar cells, we take the dye, diluted dye, and then dilute it with water or alcohol, and then we find what is the absorption of this dye. So you will take the dye in one of the cuvettes, and then you can take a simple water in another cuvette. So which will act as a baseline. Whatever is the solvent that you're taking in this dye, the same solvent you can take it in the another cuvette, and so this becomes the reference light I0, which gets completely transmitted. I mean 90% gets transmitted, except the parts that is absorbed by the cuvette and the solvent. Almost everything gets transmitted over here. And let's say this also you're giving reference light I0, but most of the light gets absorbed in this part, and let's say small amount I is getting transmitted. So we have two sensors which senses what is the light that is reaching this point. So what we have is that we have a reference light and we have the transmitted light from the solution. The similar setup can be done for film as well. You can place this film in this position, but the arrangement will be a bit different. In this we have spectrometers which can measure for solution as well as for film. So at one point there will be a setup for holding this cuvette, and another part there would be a setup for holding films. So you can put the film onto this spectrophotometer, and you can put a similar glass over here. so that all the baseline correction will be done. Baseline correction in the sense, whatever the glass absorbs, you have to consider that also when you have to find what is the exact absorption of your material. So once you have these two quantities, you can write absorbance in terms of it is given by the formula. Absorbance A is given by the formula log to the base 10 1 by transmittance. Now from here you can see what is transmittance. Now transmittance here is basically the amount of light that is getting transmitted, that is I, divided by the reference light. So the amount of light that is getting transmitted divided by a reference light, when you take the reciprocal of it, you get absorbance. Or if you are taking it as a factor in 1 or percentage, then whatever is a 100 minus transmittance would be your absorbance. But typically the Beer-Lamberts formula, Beer-Lamberts has a different formula as well, but the general form in which we write absorbance is A is equal to log to the base 10 1 by transmittance, where transmittance is given as I by I0. So you will get A as log to the base 10, I0 comes to the top and I to the bottom. So this will be the form. Now the proposals that were made by Beer and Lambert was that the absorption of light is directly proportional to the path length inside the solution or in the film. So generally in the film the path length will be going to be very small in the terms of probably few micrometers or even in nanometers, but here the distance is this distance d, or the path length, so or L, whatever you want to call it. So the L, this is the L. So this is the length through which the light is going to pass through inside the solution, how much length the light is going to pass through. So that that is one parameter on which the absorption of light will depend. Another parameter is the concentration of the solution. So concentration of the solution is the next parameter. We can call it C, and then the formula for absorption is given as coefficient of absorption epsilon into L into C. This is the path length, this is the concentration. The absorption is connected between the path length and the concentration using the coefficient called as absorption coefficient. So this is the basic formula for absorption of light by a semiconductor or a solution. So we'll just look at a simple question, a simple problem, and probably with this this idea will be a bit more clear. So let's look at this question. A solution shows a transmittance of 20% when taken in a cell of 2.5 centimeter thickness. Calculate its concentration if the molar absorption coefficient is 1200 dm cube per mole per centimeter. Now it's given that the solution shows a transmittance of 20%. So what is given is that T, which is equal to I by I0, where I is the transmitted light, and I0 is the reference light. Therefore it's given it is 20%. 20%, which is 20 by 100, that is 0.2, right? Now what is the other parameters? It is given that the thickness of the cell is 2.5 centimeters, which is the path length. So path length is given. Calculate its concentration. So concentration, we need to find what is its concentration. Absorption coefficient is also given in this question. So first let's find out what is the absorption here in this case. So absorption A is given as log 1 by T, which can be written as log 1 by 0.2, which is log 5 to the base 10. So let's calculate this. This comes out as just a moment. Yeah, it comes out as 0.698. The value comes out as 0.698. Now let's look at what is the concentration. So the formula for absorption can also be written as A is equal to epsilon L into C. So from where I can get C is equal to A by epsilon L, that is 0.698 divided by 12,000 into 2.5. This will come out as let me just calculate. This comes out as 23.266 into 10 to the power minus 6 moles per dm cube. Mole per dm cube. So this is the concentration of the solution that we have taken. So I hope this is clear. If you want, maybe I think let's do one more question. Let me read out one more question. A solution of tryptophan tryptophan as an absorbance at 280 nanometer of 0.54 in a 0.5 centimeter length, 0.5 centimeter length cuvette given the absorbance coefficient of tryptophan is 6.4 into 10 to the power 3 liters per mole per centimeter, what is the concentration of the solution? What is the concentration of the solution? So this is the question that we have, and let's find out how can we do it. So it's a bit more direct question. So only thing is that it is given that the absorbance at 280 nanometers. So this is a value which is a bit tricky. We'll discuss this as well, why this is given as 280 nanometers. Is 0.54. So they have basically taken a wavelength, a particular wavelength, and at that particular wavelength you get absorbance of 0.54. So A is given as 0.54, which is equal to epsilon L into C. The length of the cuvette is given as 0.5 centimeters, and the absorption coefficient is also given over here. So you can substitute all these values. So C is equal to 0.54 divided by 6.4 into 10 to the power 3 into 0.5. Now when you do this, when you calculate this, you will get the value as 1.68 into 10 to the power minus 4 moles per liter. So that will be the final solution that you will get in this case when you divide this, because the absorption coefficient is given as liters per moles per centimeter. When you multiply it with the length, which is 0.5 centimeters, you will get it as moles per meter cube. Absorption doesn't have a unit, so absorption is generally expressed in as a percentage, because and therefore it is unitless. Now let's look at what is the significance of this 280 nanometers. So in this question, it is not used in the calculation part, but let's look at how it is represented in this photospectrometer. So generally when we do this analysis using a photospectrometer, what we get is that very similar to the solar spectrum. I mean, how we plot the solar spectrum, we'll actually get absorption as a function of wavelength, so you can measure from any wavelengths. Generally the measurements in these meters starts from 200 nanometers. You can go all the way up to something like 2500, depending upon the instrument and its facilities available. Some instruments they give measurements only up to 1200 or 1000 nanometers, but some more sophisticated ones can go up to 2500 nanometers or even more. So basically it is the ability of the of this source, which can, the source and the detector, source has to produce light in these wavelengths, in different wavelengths, all these different wavelengths, and you will get some kind of a waveform. Let's say something of this sort. Some region of the light is getting absorbed. So from the absorption spectroscopy also there are a lot of things that you can tell from the absorption spectroscopy, because let's say if this is the waveform, so the light is getting absorbed at this region from a few 300 nanometers or somewhere to up to, let's say, 600 nanometers, and the rest of the light, I think, I mean, it's going at 0, and which means that there is no absorption. So the band gap, basically you can plot a tangent over here, and you can find what is the last value of lambda for which your light is getting absorbed, and from there you can have a rough calculation of what the band gap of the material is. So let's say if it is around 600 nanometers, then you can use the equation energy Eg is equal to 1240 by lambda. So from there you can find what is the let's say if it is 600, and then you can cancel this out. You get something near to 2 point something, right? 2.1 or 2.2 in that range. Somewhere in that range you will get your lambda. No, sorry, not the lambda, electron volts, which is the band gap of the semiconductor, because the light is getting absorbed only in this range, and the final value of your light that is getting absorbed will correspond to the band gap of the material, because all those photons which is having energy less than this region will not be absorbed by the material itself. So this can also give an idea, the absorption spectroscopy can give an idea of what is the band gap, but this is not the actual way in which you have to find the band gap, but you can get a rough idea of where the band gap of the material lies from by looking at the absorption spectroscopy. So that is another advantage of this spectroscopy, and you can also find what is the absorbance at various wavelengths, or how much amount of light is being absorbed. So that is the basic idea over here. Now in some of the spectrophotometers we have only taken into consideration now while doing these calculations, we have only taken into consideration the absorption and transmittance, but a small amount of light can also be reflected by these materials. So reflection is another phenomena which has to be considered. So modern spectrophotometers also has a provision for finding what is the reflection or the reflectance, and then it subtracts that value also from the absorption. So that is the advantage of some of the modern spectrophotometers that come in the market. So they can actually find what is the reflected amount of light, and then it can subtract that value of light also from the absorption, which gives you a precise absorption of the material. So I think with that we'll wind up this session. Thank you guys. I hope it is clear.